Good afternoon, everyone. Please be seated. So this second talk is about to start. And this is about no time to idea about profiling import time in Python by Daniel. Please give a warm welcome to Daniel.
Okay, hi everyone. So yeah, my talk today is no time to idle about profiling import time in Python. So first, a little bit about me. I'm a production engineer at Facebook. I've been there for over a year now. I'm from Townsville, but I went to Melbourne for university, and these days I live in the US. I gave my first talk ever last year about context managers, so I'm super excited to be back. For the sake of accessibility, you can download the slides. You can download the slides using that link in the corner, in the top right corner. All the code is text, all the images have alt text. I know my website sounds like deport me. I made that same joke last year. I should get a new domain. Oh yeah, and following Brandon Rhodes' talk yesterday, I'm going to start the talk by saying thank you for coming, and then I'll do it again at the end. Okay, so what's the problem? The problem is your imports are slow and you don't know why. So why are slow imports a problem? Mainly command line tools. So anytime a human person is waiting, that's bad. And beyond that, slow import time is impactful beyond just a single run. Users might want to print a few layers of subcommands and get their help messages before they even run the actual command they're planning on doing. So if your time to print help message is like upwards of 30 seconds, which is real from personal experience, it can really add up. Additionally, it makes your development time worse. You know, Python is valuable for its like fast iteration time, so this makes it substantially worse. So how do we fix this problem? Step one is to understand it. So my aim for this talk is for you to walk away with a collection of various different tools for collecting, visualizing, analyzing, and then ultimately acting upon the import time data that you get. Not everything might work for everyone, but hopefully some combination of things will be good for your use case. So let's start with an example. So here we have a program, and it imports two modules, small and large. And then this is small and large. So we can see that large takes 10 times as long to import than small. So I'm using like sleeping essentially to emulate slow imports instead of showing you like a 500 file program. So yeah, this is obviously a contrived example, but yeah. So let's see how long it takes. There you go. So that took 11 seconds to run. And then give or take a little bit of inaccuracy in sleeping and other imports. So sweet, we know how long it takes. But there's a big problem with this output, and it's that it's just this. Here in our example, it's obvious what the actual problem is, but that won't necessarily be true for a more complicated program. So we get all of our import time information collapsed into a single number. What we really want is import times for each of the modules in our program. So how do we get import times per module? There are a few different approaches. So first, you can time each import directly in your code. The first thing you Google on import profiler in Python is essentially this. It just gives you a context manager that does this, and you have to wrap every single one of your imports manually. There's a lot of manual work. It doesn't necessarily work if you can't like change what you're importing. And you have to roll your own logic regarding cumulative versus non-cumulative import time, which we'll get to. You can modify the import machinery, which is what the docs call it, essentially modifying your finders and loaders. Or probes, question mark. I didn't go this deep. I think it's beyond the scope of the talk. So prior to Python 3.7, these were the majority of your options, nothing included by default. But enter Python 3.7, we have some support for this baked into the language. So there's a runtime flag you can use called import time, and it will print to standard error for each module, the import time, and the cumulative import time of that module. You can also use that environment variable to do it. So yeah, this is the first officially supported import time profiling, and it's done directly in like the C, which is really cool. Yeah, so like a big thanks to the community and the 3.7 contributors for that. Like it's a really cool little addition. particularly to Victor and Inato, who put the whole thing together. So let's see how it works. So we're back to our example. Now let's run this with the 3.7 import profiling. And this would also work. So let's run it. OK, now that's a lot of information. It's a lot of imports. Most of these things we're seeing are all of the default Python imports. The things that we actually care about are only the bottom 3. Everything else is all imported by default, no matter what you're doing. So let's just throw all this out for now. So let's have a little closer look at what we've got here. So the order is a little bit weird. It's essentially a function of the way the depth first search in our importing works. So we see the deeper imports first, and then we print import times as we go back up the stack. Yeah. We also have this self versus cumulative column. So you can see for the time module, which is a leaf essentially, the self and cumulative are equal, because time itself doesn't actually import anything. Whereas small, you can see there is the self time and then cumulative. And cumulative is just the addition of itself and the time module, right? So it's really handy being able to see what each module on its own actually costs without everything it imported itself. And we also don't get to see main, but we could get that easily ourselves. So great, that's it. We can see the largest import. Let's call it an ALC next year, right? No, we can do better than this. And here are all the imports again, but bigger, in case you're curious. Oh, but I'm not on 3.7. Should I just leave the room? No, so only 30% of people using Python 3 are even on 3.7. I personally do 3.6 all day, so I'm in the same boat. And getting to 3.7 isn't necessarily easy either. So I've got your back. I hacked something up yesterday, and it is a hack. I find every loader and then wrap the exec module function. Don't worry about it. You can have a look at it on the GitHub. And it works for 3.4 plus, which is 98% of people, which is much better, I guess. Yeah, so let's say you had this program. You would convert it to this. And what it would do from that point is it would print out the import times. So this is what it looks like in 3.7. And then here's what it would look like using my thing with 3.6. Note that you don't get time, because I had to import time in this module for this to work. So it was already imported. But everything you import after that point, you will get this output. Notably, the timing information will also probably be a little bit off, because I'm doing it in Python instead of C. But in my testing, it was pretty close. So sweet. So the default output is actually pretty good, but we want to try and visualize this. Visualization is super powerful, and it allows you to more easily see what your problem is immediately. So a classic way of showing this sort of cumulative stack-based data is a flame graph, which there was actually a talk yesterday that mentioned them, so that's cool. They're commonly used for call graphs, but I'm going to initially use one for this import information and see if we can make it work. It doesn't necessarily convey all the information, which we're going to get into later, but Python itself exposes this information as a tree, so we're going to roll with that for now. So step one is to, convert this data back into a tree, and then by using this tree, we can sort of output the information again in whatever format we want. So we'll run our program and collect the standard error, and then we'll get the data into a tree. So this is something I sort of just hacked together. It's very basic. I'm constructing the tree, and then I navigate it and output the information again. This is my basic output debugging, just so you can show that I'm not making this up. And I do actually get it into a tree format. That's actually worse than what Python gives you, so we'll move on. So let's format that into something useful. So I made it be able to import, export flame graph information, and then we can get that. And this is essentially what Linux perf profile is output. And then we can put this into, this is what it looks like. Don't worry about it too much. And then we can put it into flame graph. So this is the same tool that was used yesterday. It's actually a Perl script. I'm a big poser. But it outputs this really nice SVG that we can use. So this is what it looks like. if you were to like play around with this in your browser, you could click on each import and it'd sort of zoom in and you could see all of that, but live tech demos are a big risk, so I'm not doing that. Additionally, I changed these sleep times from like 1 second and 10 seconds down like a few orders of magnitude. Otherwise, you wouldn't be able to see anything else but small and large because they would eclipse the size of all the other imports. Yeah, so essentially you can see that we've got our small import here, and then you can see that small import's time. Oh yeah, and then, so moving on though, while researching, I came across a great tool called Tuner. It's very similar to FlameGraph, but it's actually made in Python. Someone posted a link to it on the Python, bugs.python thread for this new feature in 3.7. Previously, it was only for runtime profiles, but then support was added for these import profiles. And big thanks to Nico, who explicitly let me use this in the talk, which is really neat. So you pretty much just take your standard error, and then you run it against Tuner, and it spins up its own little like Flask web server. And this is what it looks like. So very similar. You can click on it, and it's got like these neat little like easing in and out animations. So I pretty much just showed FlameGraph earlier to like pay respects to the classics, but this is like what you should be using probably these days for Python. But is a tree even the right data structure? We've been ignoring a major thing so far with how importing actually works in Python, and it's that they're not really a tree, they're actually a graph. In some ways, importing is a tree, but in other ways, it's not. So let's dig into that. So here's some pseudocode for how importing works, essentially. You have your sys.modules, which is a list of all of the modules that you've imported so far, and then you have this recursive import function. So per module, it will go and import all of the things that it imports recursively and add it to the list. So if you get to a module that you've already imported, you won't do it. So in that way, modules are actually a singleton, which is like sort of a cool abstraction that Python offers you. So let's try and visualize this. So remember that first example, we've got our main, small, and large. Main imports small and large, and both of them import time. So let's look at how that works. We've got the main, it imports small, small imports time. Now, main imports large, and then large imports time, except it doesn't really, it's already imported. So in that sense, imports are a tree, right? Well, that's only in terms of loading. It still navigates this import graph, and it, in a sense, only the first visitor actually imports the module, the rest just use what's already loaded. So when considering which module to investigate, a tree structure sort of lies to us. In that it's almost unfair in a way. So small cops the cost of this time import, whereas really large should also sort of be sharing the responsibility. So obviously, when we look at the output that Python gives us, we can see that pretty clearly, that like from the self and the cumulative time. So we can see that small's like import time is overreported. But what we can't really see is that large's import time is underreported in that it's not including the time import. So we really need a graph to properly convey this relationship. So there's a super cool open source project called PyDeps, and a big thanks to Bjorn, who let me use this as well for this talk. It essentially navigates your module import graph and then gives you like a nice visualization for it. So here's how you'd run it. Max Bacon is apparently to do with Kevin Bacon, and it's about 6 degrees of separation. I think it might be like before my time, but it's the number of hops that you are willing to navigate in your tree. 0 just says infinite hops. So by default, your imports, like the default imports are excluded, which is actually really nice. So we only get the things like we have written. So let's go back to our example program. Now, this is what PyDeps gives us. So we can see our main, it imports small and large. But as you can see, these nodes are all just equal size. We don't have any import times. So this feature actually isn't present in PyDeps right now, but I forked it and added this functionality. I have yet to merge it back in, but I'm planning on doing that. So hang tight. So let's see this output with import times factored in. Right, there we go. So immediately you can see that like large is very obviously the worst module, And we should be sort of looking to that to see if we can cut the dependency or whatever. Yeah, sorry, just a second. But of course, this import structure is actually still just a tree. So let's go and see a graph. And for that, we're going to need a more complicated program with a more complicated import structure. So we've got our main. It imports two modules, 1 and 2. One imports from these other things, funcs and constants. 2 only imports from constants. And then these are those 2 modules. So just to briefly explain what we've got here, funcs has 3 different functions in it. Constants exports a single constant. I also put some sleeps in there to emulate like expensive instantiation or something occurring. Yeah, so let's look at the import graph for this. So this very clearly visually outlines what we're working with. And now let's see that with import times factored in. Just a second. I'll let you digest that. Sweet. So our intent is to find imports to focus on removing. So obviously, we should just go for constants, right? It's clearly the largest node in the graph. Why don't we start there? But there's more to it than just import times. There are other things that we need to take into account when trying to pick which module is the best to remove. So another thing to consider is connectedness. So what I mean by connectedness is, effectively, my metric for connectedness is how many other modules import this module. So if a module is imported a lot, it's going to be hard to break that dependency because like 10 other modules might depend on it. Which obviously means like greater risk, harder to move things around, that kind of thing. So we can see that 2 things import from constants, whereas only 1 thing imports from funcs. But our node size doesn't really take this into account. So using another easy addition to PyDeps, you can get this information. This was actually super easy. The information was already there. Just had to print it out. So what can we do with this? So like I said, we want a graph where the largest node is truly the best place to start fixing. I'm sort of trying to produce a metric for people more than just like a number, as in optimized for human effort, rather than just like raw performance wins. But you could obviously tweak these for whatever your use case is. So let's try and adjust the size of our node based on connectedness. So this is obviously a super simplistic, really basic formula. I'm not a mathematician. It probably needs some constants or like some like exponential factors or something like that. But it displays the basic relationship. So the more times a module is imported, the smaller we're going to make the node. So it's not really a node cost so much as how good of a candidate for inspection is this node. So let's look at the graph adjusted with this information. So you can see here that funcs is now larger than connectedness when we take this information than constants when we take this information into account. This implies that despite funcs being a smaller import in terms of import time, it's a better candidate because it's not so heavily connected and we might be able to remove it more easily. Again, this is just a basic formula, but these are the kinds of factors we're trying to think about. On the contrary, I should actually mention something else that a coworker pointed out like just a few days ago, is that within the realm of a single program, this is true. But if, for example, you have a library that is used by 10 different binaries, the equation sort of flips on its head again. If you can like half the import time of a library that's used very widely, that's a very impactful change. So that's another thing you might want to like factor into your calculations. So specifically, if you were to improve the import time of a module that's used by like 10 different binaries, that's like a 10x win, which of course makes you a 10x engineer. So, and that's what we're all trying to be. So this is all getting pretty good, but we can do even better. Oh yes, and yeah, there are the 2 side by side. Cool. So there's another thing I want to consider, which is unique attribute access. So thinking back to the code, we only get 1 thing from constants, which is pi. But we get 3 different things from funcs. So that means that funcs, despite being only 1 connection, is more heavily connected. So it would require a lot more effort to try and like take out these individual pieces that we're using. Whereas for constants, it's only 1 thing we're relying on. So why unique access? When we're thinking in terms of runtime profiling, we generally care about like number of accesses. But we're trying to look at what is the easiest thing to try and remove. And additionally, again, imports are like single time. Unique attribute access isn't necessarily a characteristic of the node, but the edge. For example, 1.py could import 3 things from a module, whereas like 2.py could import 10. I wanted to really visualize import time just on the node because it's easier to see, but you could obviously add edge costs to your like edges and make them like thicker or something. So here we have our graph before. We can see that 1 and 2 only import 1 thing from constants, whereas 1 imports 3 things from funcs. So let's try and get another formula together. So here we have our import time. I've got number of times imported plus the unique attribute access on the bottom. Again, this is obviously like a really shitty formula, but it displays the basic relationship. Cool. So when we like do these number crunching, we see that constants instead of funcs is all of a sudden the better candidate. So we should probably start looking there as like, oh, maybe this is the module that I want to focus my efforts on and try and remove. This indeed, like this mirrors things that have happened in real life. You'll have like a really expensive import and realize you only import 1 thing from it, and it does like 100 different things. So you're going to try and just get that one little piece you need and move it out, for example. Cool. So sweet, we have all of our formulas and all of this stuff together. We have like a sort of decent metric on trying to figure out what place we want to start with our program. Of course, there's always room for improvements with these metrics. There's definitely a lot of room for improvement here, but we've got a pretty good base. So what do we do now? Of course, you want to like do a bit of investigation to make sure that what you're trying to fix is actually feasible. So first thing is restructuring imports. It's very common to have like a file like helpers.py, and it has like 100 different functions in it, and all of those functions have their own dependencies. And then everything will import from that and cop the runtime cost, or the import time cost. So what you can try and do is break out the components into like more modular modules, and that way the import times will decrease. Yeah. Another big one is you want to avoid doing work at module level. This is like a super big one, and it seems obvious, but lots of people like make these mistakes where they will instantiate an object that they don't realize has like a runtime cost. So what you want to try and do in these cases, if you really want to define your thing at module level, is try and do lazy instantiation. So you could wrap it in a class that only instantiates on first use. So instead of doing this, oh shit, I forgot the module. I meant to change that method name. Imagine you have this class. It's expensive to instantiate. So instead of doing this in your module, where you just go e equals expensive, try and do something like this. This is obviously a lot more code, but we take in the class args, quargs, blah, blah, blah. And then whenever we try to actually access something from this, that's when we will instantiate it. So we don't do our expensive instantiation at module load time, but on first attribute access. There are other things we can do. We can do lazy importing. So you would essentially, for example, you could try and import a module only in the function that actually uses it. This is like a common strategy for CLI tools with subcommands. So you only import each subcommand potentially, and it would be defined in its own separate file. And then there's also demand import. So this is like a really cool tool that was developed like as part of Mercurial. Mercurial is like sort of famously written in Python instead of like C, like Git is, and still manages to be really fast. And some of the ways it does this is using things like demand import. So it essentially just takes all of your imports and does every single one of them lazily. So it's like a big hammer to use. So if we go back to our example, we can change it to this. And then if we were to run it, if you remember, 2.py printed the value of pi. But we don't see that now because we never actually access anything from 1 or 2 in this program, so they never get imported. If we were to access something, though, all of a sudden we would see this, where it's delaying the import times, and then we trigger those imports, and they occur later down the track. In general, this is better for things where humans are waiting, like command lines. Whereas if you're using a server, you might not want something like this because your first request for each of the endpoints will randomly be much more expensive than the rest, and your alarms are going to fire and people are going to be sad. So in a server, just import everything at the start. It's more for like humans, in my opinion. So yeah, we made it. That's all of the stuff we had to talk about. We talked about how to get import times in 3.7 and below. different methods of visualizing the data in terms of like a tree and a graph, different ways to sort of try and define what is a good module to target, and then some suggestions for how to fix it, such as lazy instantiation, like lazy importing, that kind of thing. So a big thanks to Lachlan for watching my dry runs, the PyCon AU team, the open source community for all of the stuff I used, and all of you lovely people for coming to my talk. That's my second thank you. Any questions? But while I'm doing the questions, I'm going to leave up this like little resources slide so you can go and like, if you're interested in any of these tools, you can use those. Thanks.
So any question for Daniel?
I'll be in the hallway as well. Yeah.
Oh, sorry. Okay, I'll come over.
Thanks, Daniel. Great talk. I'm just wondering, what are some of the use cases that you found you have to go through your imports and optimize them? What's the sort of delay you get using some of the CLI tools? Just want to have a feeling about the actual use case that I actually need to dive deep into this.
Sure. So I use like CLI tools at Facebook that link in just an absurd number of different things. On like a bad day, I will have tools that take 30 seconds to print the help message, which is obviously crazy. And that's due to well, obviously we use these to try and figure out what it is. It'll be like any combination of these different things, like bad customer modules that are doing things at import time. We also do some like crazy stuff with Cython and loading in modules and all that kind of stuff. So it could be any one of these things, but for internal reasons, these tools don't actually really work very well for us, but like it's an ongoing field of research, I suppose.
Any more questions? Okay, let's give a warm welcome, and there's